Okay, so that fires up the recording. I think this is where we wound up last time. This is the absorption refrigeration cycle. These slides were put together by Train, who supposedly knows quite a bit about this. And, you know, I guess I can take my mask off since I'm the only one in here. So we'll go through these, and then there's another presentation I think I've sent you on the economics. They do an economic analysis to kind of give you an idea when this absorption type chiller might be economically preferable to centrifugal chiller. Aha. Now I got a mask up. That's okay. Come on in. All right, so this is slide 25 if you're following along on the email. And I have discovered a new presentation mode here. I'm going to try. I did this. And this will show the notes down at the bottom. And on some of these slides, these notes are pretty good. And I can make this bigger so everybody can see better. Try this. Get fired up here. Okay, so this is kind of what we talked through before. And all of these components make up the absorption chiller. And, you know, some of these are common to the centrifugal or other types of chillers. And, you know, quite a bit of this equipment really is not. I mean, we don't have the generator and the absorber and some of these pumps. They take the place of the compressor in our typical vapor compression cycle. And of course, our pressures are much, much lower in the absorption machine. I mean, we're talking the whole machine is at a vacuum, and it's really a hard vacuum in the evaporator because we want this water being the refrigerant, we want it to evaporate on the outside of those tubes at 40 degrees. And if you look down, I think it's what, 0.12 PSI. Well, 14.7 is atmospheric pressure, you know, at sea level. And so at 0.12, that's a pretty hard vacuum. And it's about 10 times that up in the generator. So, you know, I think it's 1.35, 1.4, something like that. So it's roughly 10 times higher. But even 1.3, 1.4 PSI is a significant vacuum. So the whole machine's under vacuum. And as we'll see, we'll talk a little bit about this today. One of the issues is having air leak. You know, you've got seals on this thing trying to maintain the vacuum and the appropriate pressures. And when we start allowing air to leak in, then that's going to be detrimental to the performance of the machine. Okay, so anyway, just to kind of, let me see, can I lock down? I don't know if I've locked down my pointer in this mode. But so this is the heating medium. This is going to be hot, typical hot water or steam. We'll see in the next presentation that they actually have direct fired units as well, that actually you just pipe natural gas up and it's got combustion burners and such built into the machine. But for right now, we're thinking about supplying either hot water or steam, low pressure steam. I think typical is like 12 PSIG steam. Hot water, roughly 200 to 250, something like that for a single stage machine. And we'll see, we also have two stage machines that require 350, 400 degrees Fahrenheit, or, you know, in excess of, I think it's something like 100-pound steam, something like that, to drive those cycles. At any rate, we're going to put in heat here, and in this generator, we have lithium, bromide, and water that has maximum concentration of water supplied to it. So, and these percents are percent lithium bromide in solution. So 58% is a weak solution, meaning it has a lot of water, and we're going to pump it up here, and we're going to put it in here, we're going to heat it up, and when we do, we're going to drive off a bunch of that water into the vapor state, and then it's going to migrate over here to a condenser, where we've got cooling tower water inside tubes, and that's going to condense. Now this is at our high pressure, someplace about 1.3, 1.4 psi-A, and it condenses, and we pile up some liquid water over here in the condenser, and then we have these orifices, and this is the pressure drop, you know, from the high side. So this is high side pressure over here, and this is low side pressure in the evaporator. So this is where it drops to like 0.12 psi-A. Okay, and so when that water goes through there, it's liquid up in this state, but that's enough of a pressure drop that some of it flashes, I don't know, 5–10% flashes to the vapor state, and that's enough to cool down the entire flow. So that liquid gets cooled down as well to roughly 40 degrees, the saturation temperature. And the vapor, you know, is just liberated into this area, and it'll migrate down to the absorber. The liquid then falls on these tubes, and this is where the chilled water is produced. We've got 54, well, they're showing 55 on the slide, okay, 55 in and 45 out, showing the 10-degree delta T. And so that water comes in inside the tube, and this 40-degree liquid water is on the outside at this low pressure, and it boils away, so it vaporizes. Well, that's nominally 1,000 BTUs a pound of heat that's being sucked out of this chill water, so it cools down. So we're showing it leaving at 45. So the liquid that vaporizes, again, migrates its way down to the absorber and gets recombined with the lithium bromide. The water that doesn't evaporate falls down in this tray, and this pump just keeps pumping it up, spraying it out on these tubes. So eventually, you know, any particular water molecule will get evaporated, but we continually have this water flow down here. So, you know, this is basically kind of a steady state situation. The capacity can change, and so that, you know, there are some transients, but generally speaking, you can think about this as a steady state process. So all of this is low pressure down through this region. So in the absorber, we have another little pump that's taking, it takes some of this 50A, which this is already absorbed, but we're mixing in the strong solution, which is 65% lithium bromide. So it has the minimum water content coming out of the generator. And we put it through a heat exchanger because we want to cool it down, and we want to cool the weak solution that's getting pumped back up here to the generator. We want to heat it up. So it's a perfect application for a heat exchanger. So we do that. And I think we're showing, we're coming at 214, we're coming in, and 135, we're coming out. But this doesn't have much water in it at all. And it mixes with some of this that does have water, and we get kind of an intermediate solution that's showing 62%, and that's what gets sprayed into the absorber. And that spray lets it mix with the vapor, and they combine up because lithium bromide and water, it's a salt, and they really like each other, okay? Now, that reaction in the absorber is exothermic, so it gives off heat that has to be cooled away, or the machine would just continually build heat until something bad happened. And so this is where the cooling tower water, we're coming out of the cooling tower at 85. And so the first place it goes is into the absorber, and it comes out at 95. So we pick up 10 degrees on this exothermal heat of reaction. And then we go up to the condenser, and so we're in at 95. We pick up 8 more degrees. We're 103 out, which goes to the cooling tower. Now, if this was a centrifugal chiller, we would show this in at 85 and out at 95, going back to the tower. So we have to have, for the same tonnage, we have to have a larger cooling tower for the absorption chiller than we need for the centrifugal chiller because we have more heat to reject, okay? All right, so let's see. Then, so we talked about this loop. This is where this is going to the absorber. We're going to mix with a strong solution here, and we're going to spray it. And then down here at the bottom of this well, this is the very weak solution that's going to get pumped back to the generator after we preheat it. We're showing 103 here, and we're showing 175. So we're picking up quite a bit of heat, and that just reduces the amount of energy that we have to put in order to boil that refrigerant off. And that's pretty much what's going on in this thing. Realizing that we're putting in thermal energy as the major energy input instead of on that centrifugal compressor, which has a big electric motor. It may have a 400, 500, 600, 700 horsepower, you know, bigger or smaller, depending on the capacity of the chiller. But that's a big electrical load. Tennessee Tech, those chillers, they've got to be the biggest motors on campus. We've got 1,500 ton chillers down there. I could do a calculation. I don't really remember exactly, but that's probably 600, 700, 800 horsepower motors. It's a pretty big motor for, you know, campus like Tennessee Tech. I don't think there would be anything larger. The generators, the emergency generators would have generators that are larger than that, but not as far as just an electric motor. Okay, so now that just kind of summarizes what we did last time, but I thought, you know, I want, and I sent a link to a YouTube video that talks about this. It's pretty good. Some of those things I like YouTube. You know, you can go find stuff that's, you know, pretty introductory and, you know, explains things pretty well. I'm going to send an email today, and we're going to have a quiz on Thursday over these videos that I've asked you to watch, and I'll send you the links again. I know there was a VFD induction motor. We had the absorption chiller. I think we've had something on centrifugal chillers. We had ASHRAE 62. We had that long train video that probably pounded you to death on ASHRAE 62, the ventilation standard. But what I'm going to do is I'm going to pick a number of questions, trying to make them simple, just trying to see if you can kind of guarantee that you've, or at least convince me that you've actually watched the videos. The point is not to make these things difficult, but my 30-something years of teaching, oftentimes things don't get done if there's not a quiz or an evaluation at the end of them. So we will do that on Thursday. It will be in YouTube. And so you will have to, not YouTube, but iLearn. You'll have to log into your iLearn account, and it'll probably be, I don't know, 15 to 30 minutes, something like that. And then we'll have class afterwards. So I warn you, but you will be getting an email on that as soon as I can get one put together. Okay, moving right along here. Let's go down. Oh, whoa. Thing kind of took off on me there. Not used to driving this way. Okay, so that is, okay, it didn't. Gotta be careful here. Okay, this is equilibrium chart for lithium bromide solutions. We're not going to work thermal problems with this, so we're not going to do this. This thing is pretty obscure. I've looked at it for a while, and I don't know that I can really do a good job of explaining it, so we're going to pass by this. You will not be responsible for that. Let me see if I can get my mouse going here. This will work better. Okay, so one of the big issues in absorption is crystallization. And this is where the water and the lithium bromide, the salt, separate, and you get a whole big clump of salt. And when you do, the thing's not going to work very well. Now, over the years, the manufacturers have gotten much, much better to avoid this. I can tell you the first absorption chiller I ever saw was on Millington, Tennessee, north of Memphis, had Millington Air Station, which was the largest inland naval base. Why there was a naval base just north of Memphis, I have no idea. But it was the largest inland naval base in the world. And this was one big flipping operation. And the Navy operated it, and they did pilot training, and they had all kinds of stuff going on in Millington. Well, I worked for a little consulting firm, and we were hired to go out and look at some of these buildings and try to come up with ways to make them more energy efficient. Well, one of the buildings I drew had this big old absorption chiller in it. And at that point, I don't think I even knew what an absorption chiller was, which is one reason that I want to pound you, so that when you get out of here, at least you'll know, you will have heard of an absorption chiller and have some kind of an idea how they operate. But I went out there and I looked at this chiller, and they, they kind of chillers kind of look alike. I mean, they got these barrel heat exchangers on them and all this kind of thing. But this one, it kind of ripped off the insulation, and it was all beat up and dented on the outside. And I asked him, I said, what's wrong with this thing? It's all beat, basically it's beat to hell, pardon the expression. And they had a sledgehammer out there next to it. And what they would do, the thing would crystallize, and down in that heat exchanger, I guess it's probably the absorber, I'm thinking. But at any rate, and it would crystallize. And in order to get the machine back going again, they would take that sledgehammer and they'd beat the outside of the heat exchanger to break the salt back up, from these large crystals into small pieces, so they could start absorbing water again, and they could get the thing back online. And over the years, it had crystallized a lot because that heat exchanger was beat. It was beat up, had dents all over the thing, hit it with a sledgehammer. So in the old days, this used to be a pretty significant problem. I think it's much better these days. How much of a problem it still is, I really don't know. But so that would be an issue if you were ever going to recommend one of these things or actually get serious about putting it in. You would want to really do your homework to make sure that for your operation, it didn't look like crystallization was going to be an issue. But anyway, so on the slide, there's a minimum solution temperature for any given salt concentration. Below that minimum temperature, salt begins to leave the solution, which leaves just big chunks of salt laying around. And then the reason I changed this mode is these notes are pretty good. You have them in your slide, but in some cases I'm going to read them, and in some cases I don't think I need to read that one to you. It pretty much is summarized in the slide, but some of them have pretty good information that is not really on the slide. So anyway, crystallization, you need to know about a little bit. Not too much, just enough to be dangerous. So what causes crystallization? And we'll have a number of slides that go through different things that can happen that can cause issues. So air leaks in machines. And so what happens is in the evaporator, which is where we do the cooling, the pressure goes up. Well, if the pressure goes up, the temperature goes up, so instead of evaporating this water at 40, maybe we're evaporating it at 45 or 50. Well, guess what? So that lowers the capacity of the machine. You can't get the refrigeration out. And so the chiller senses the leaving water temperature going up, and that adds more thermal input. And if you keep adding thermal input, that can lead to crystallization. Now let's see what this note's pretty good. Let's see. So I think it says a lot of what I just said. So vapor pressure increases, air gets in the machine, higher evaporator, temperature reduced capacity. So controls sense this, and we increase the heat input. Then results in increased concentration to the point where crystallization in the heat exchanger could result. Today, with DDC controls and automatic purges, we can stay away from the crystallization region. So these machines today, they can sense when these air leaks occur and pressure starts going up, and they have automatic purge units that can pull the air back out of the machine. And they can even call you on the phone and say, hey, you have a recorded message where you call your favorite chiller technician, say, hey, I got an air leak, come fix me, that sort of thing. And you can monitor the runtime on the purge and stuff like that to give you an idea if you're developing a problem. So that's air leaks. And I don't know. I stuck one of these general slides in after every one of these slides. I don't know why. Just to make the deck longer, I guess. But anyway, just in case we have one if we wanted to refer back to the cycle. Okay, second reason. What causes crystallization? Low temperature condenser water. Okay, so, when it's not so hot outside, depending on your cooling tower controls, if you run your cooling tower fans, you can make that condenser water temperature colder than 85. And, we showed on the slide 85 coming in. Well, if it's a day you're running chiller, but it's really not all that hot outside, you've got big buildings with central core areas that require cooling all the time. I mean, you can drop your condenser water temperature to, 60, high 60s, 70, 75, whatever. And if you get it down too low, this can lead to crystallization. Now, it's interesting, on a centrifugal machine, you often want to do that to reduce the energy on the chiller. And that's kind of an area of discussion and amongst chiller plant operators is, how hard should you run your tower fans, because that's more cooling tower energy, in order to reduce chiller energy on the chiller. Well, the chiller is the biggest motor, but you have to kind of go through an exercise, and it depends on climate and some other things. So anyway, so let's see what so low condenser water. Low condenser water temperature with high load, dilute solution returning cold enough causes the concentrated solution going to the heat exchanger to crystallize. So the concentrated solution is coming out of the generator. That's how it got concentrated, is we drove the water out, because when it's concentrated in terms of lithium bromide. So we have a lot of salt and not much. So that's probably the 65% solution coming out of the generator going back to the absorber to recombine. So, okay. So let's see what we got here. Excessively cold condenser water coupled with high load condition. Another way you can approach crystallization. The colder tower water causes the temperature, the dilute solution returning to the generator to drop. Okay, so this is dilute solution returning to the generator to drop. Then the dilute solution comes into the heat exchanger. It cools the concentrated solution coming from the heat and crystallization. So yeah, so you get the dilute solution going up colder than it should be. And so then that causes the strong solution to crystallize at the heat exchanger. Okay. And there's my general slide again. I don't know why I put all this. Yeah, some days you just do crazy things. Okay, another thing that can cause crystallization is an electric power failure. Now again, these things are supposedly better in today's machines than they were in the older machines, but still these are issues that have to be dealt with. So normal shutdown allows for a dilution cycle, which lowers the concentration throughout the machine. Any place that there's a high concentration, which I guess high concentration of lithium bromide is coming out of the generator. And then it allows, and then this is for a normal shutdown, and then we cut off all the heat and the machine can cool down. Without dilution, the chiller could experience crystallization. Units today have methods to avoid this possibility. So how do they do that? Well, let's see. So let's see, the first thing we've already said, during dilution cycle, solution concentration is lower throughout the entire chiller. When power is lost, normal dilution cycle is gone. Unless some other actions taken as the machine cools, those areas where strong solution could potentially crystallize. This is more likely to happen when the chiller is operating at full load. Today, manufacturers have several methods they use. So that doesn't really say exactly what they do, but they supposedly have dealt with that. Okay, here's my overall slide again. Moving on. Okay, so how do we manage this? Microelectric controls, power shutdown protection, and automatic purge are kind of what's been developed over the years. And of course, this is train, so they're going to push the train horizon, which is their absorption chiller. Microelectric controls for most manufacturers today have improved the monitoring control of the cycle to the point where controls will not allow the machine to operate under conditions that will crystallize the machine. Power shutdown protection is typically provided as a standard feature on most absorbers today, although it's handled different ways. Train horizon unit requires absolutely no backup power and uses a combination of normally open valves to put the unit in the gravity-fed dilution cycle. So a normally open valve, the valves are a lot of times spring-loaded, or even if it's an electronic valve, it'll have enough power storage that it goes, if you take power off of the valve, it goes, a normally open valve, if the control system goes down, the valve goes open. You can also get you can buy normally shut valves as well. So, you might have a situation where you have to make sure that, well, if power goes off, we got to close this valve. So you just put a normally closed valve in. Lose power in the control system, the valve, they're usually spring loaded or something. So they have their own energy source right there, and bingo, the valve slams shut. Or in this case, the valve slams open. So I want to make sure that you get that terminology, normally open, normally closed valves. Train horizon unit equipped with a fully automatic purge, able to sense the amount of air present in the machine, remove it immediately before it can cause any damage to the machine. Purge times are recorded on the unit controller, so the operator can be warned if a large leak is present. Purge can even communicate with the unit controller so that in the event of a large leak, the unit can take evasive action to ensure it operates safely. And so that control system these days can be configured to send a text or call somebody, or let somebody out there in the world know that there's a problem. Okay, so corrosion inhibitors. So lithium bromide is a salt, and salts and steels, cause corrosion together. And so, yeah, I'm certainly no corrosion expert, but so the point is, I'm not going to ask you particularly nitrate, chromate, what's that, molybdenate, whatever, and all this. But I want you to realize that there is potential corrosion issues, and they have inhibitors, and this is another operational issue that you have to be aware of. Okay, inhibitors are used with lithium bromide charge to control the corrosion action lithium bromide on steel. Inhibitor affects the corrosion reaction to form magnetite, which I know is Fe3O4, because I've run into magnetite like in power plants and that sort of thing, which coats the steel surfaces, protects them from lithium bromide and other compounds. So it's interesting, in the power plant, magnetite can build up in the steam lines, and it's hard, and it doesn't give. And so if they take a unit out of service, the steam lines all shrink a little bit because they're not, they cool down, and so it causes a compressive stress on the magnetite, which cracks it. And then when you fire the unit back up again, the steam lines get hot and the steam goes through there, and it takes all that cracked up magnetite through the turbines and causes damage on the steam turbines. Anyway, Not that you guys are worried about that, but anyway, magnetite shows up. It's normal rust is Fe2O3 and magnetite's Fe3O4. So it's the first cousin of normal rust, but it has different properties. Two-stage absorption. Okay. So two-stage absorption, we actually have two generators. Okay. And two-stage solar require higher intensity energy, such as, 115 PSIG steam with a 347 saturation temperature or 350-degree water. We hadn't talked about COPs yet, I don't think, and we will a bunch, especially in the next presentation. But a single-stage absorber, like we've been looking at, has a COP of 0.65 to 0.7. How bad is that? Remember what COP is, it's dimensionless, so you put the numbers in the same dimension, but it's the cooling effect, could be in tons or probably BTUs per hour, divided by the heat input. Now, a good centrifugal chiller, that number is going to be between 5 and 6, which means you get 5 to 6 units of cooling for every unit of energy you put in. Well, this old absorber, this single stage absorber, is going to give you about 0.65 to 0.7 units of cooling for every unit of heat you put in. Wow, that's kind of a big difference. And so, absorbers are not just to be used every place. It has to be kind of a special situation, as we'll see. Now, the two-stage units, and the single stage unit only needs 195 to 230 or something degrees Fahrenheit input to drive the cycle. This two-stage beast requires 350 to 400, and so you gotta have something much, much hotter to make it go, and you get your COP up to a whopping 1.2. So hey, it's much better than the single stage, but still, in the world of COPs, 1.2 is not great compared to the vapor compression cycle. So you need to know that. Knowing these COPs is kind of important, so you need to know that. Okay. So let's see. And he's got two slides here that are really kind of stupid if you ask me. But anyway, this is just referring to the Carnot cycle. And basically, if you look at the refrigeration cycle, the bigger the temperature difference, the higher the potential COP is what this is saying. And I didn't put the Carnot refrigeration equation up there in terms of temperature, but what for refrigeration, it's what I think it's T low divided by TH minus T low. Yeah. And for the heat pump, it's TH minus TL. But anyway. So there's that. And this next slide is just stupid. So you can look at that and read it, but I don't care. Most of these slides are pretty good, but anyway, this one's not my favorite, that one. But now let's take a look at this puppy. Good Lord. Now see, I'm not going to do this to you. If I was really a mean instructor, I'd give you some kind of a homework problem that you had to work through this thing. I don't know that I could do that, but it's a mess. There's crap going everywhere in here. So if you look at it, so here's, make it as big as I can make it. Let's see it. Okay. So here's my steam fired generator. So this is where my high pressure steam is coming in. So this is 350, 400 degrees coming in here. And, this is initially a weak solution being boiled off. The water is being boiled off, so we're making steam. We're just making higher pressure, higher temperature steam over here, okay? And it's going to go over to, so this is the first generator, and it's going to go over to the second generator. And so this stuff, this is well up in the 300s. They don't give temperatures on this, but this is hot. This is hot vapor, saturated vapor coming over here. 350 or something. So it is the energy source for the second stage, or the low temperature generator, okay? And so this is just steam, saturated steam comes in, and so it starts transferring heat, because this solution is much, much colder. This is still, probably 175. So then this steam condenses like crazy and heats up this solution so that it can boil off more vapor. And so this vapor then condenses, this high pressure vapor condenses, and it then comes across, as well as the vapor that's generated in this second generator. So all of that vapor comes over here to the condenser, and then, we're back into kind of our typical ballgame, and so, then this is our liquid line. They're just showing it a little bit different, but it feeds the evaporator, where it sprays and it evaporates, and it goes down to the absorber, and there's that spray. And here's our cooling water. So it comes in and goes through the absorber like before, and then goes through the condenser. And then they put a purge. They showed a purge unit on this. So they've added some other stuff, but so we pick up some complication back here. Let's see. So this is, let's see. So what have we got? Man, this thing, they should put some more arrows on this thing, if you ask me. Here's our strong solution coming out of the low pressure for the second stage. So it's coming down here, and we've got a high temperature generator pump. So it's pulling some of that stuff down through here, and that's getting pumped. So we got heat exchangers and a bypass on the heat exchanger. So, we can come up through here, we can come down through here. This is, I'm not sure what this red stuff is, to be honest with you. But anyway, we're circulating the strong solution back to the absorber, where it picks up the vapor, and then we're pumping out. We're pumping out here, we're pumping it back up there, and then we pull out of here and come down and all that sort of thing. So, I don't expect you to have complete understanding of all of these flows, but I wanted you to realize that there is a two-stage machine. And in fact, years ago, we had a guy that taught for a couple of years at Tennessee Tech, David Ivester. David Ivester had gotten his PhD at University of Tennessee and done his research at Oak Ridge. And his research was on triple stage absorption. So if you think the two-stage cycle is bad, well, let's hang one more stage up there. And I have even heard of people that, I don't know if they've ever built one, but at least have done, computer simulations on a 4-stage absorption cycle. So there's been lots of research done into this over the years. Okay. Let's go back down. Magnification. So let's see what they say. Well, we'll see what they say. Cycle diagram, horizon 2-stage, steam-fired absorber chiller. Notice that we now have an additional 1st-stage generator. This generator is fired with a higher temperature pressure steam. COP is greater, 1.2, single stage. However, remember that, okay, this is kind of interesting. So they're assuming here that you're running a boiler separate from this in order to get your steam. You got to get it from someplace. So I say, however, remember that boiler losses are not considered in this COP. Generally, when you compare the direct fired 2-stage COP 1.05 against the steam fired COP, the direct fire uses overall less energy. So we'll see in the next presentation, we'll have some diagrams of their direct fire unit. And they're saying it has a COP of 1.05. And when you take the boiler losses into account, the 1.05 is better than this steam-driven two-stage. Interesting. And we'll have some COP numbers on that, but I don't want to jump too far here. Okay, we're getting close to the direct fire. Oh, we've already seen that. Oh, okay, yeah. Oh no, oh, I take it back. Now, this is the direct fire unit. So let's take a look. Let's blow it up and then we'll read the notes. Yeah. About lost my mind there for a minute. Okay, so direct fire generator. So, we're piping natural gas into this. We got a burner and all this. And this is our, let me see, we're generating water vapor out of this. So this is weak solution. It's easy to get confused. Okay, so, and we've got some exhaust gas. So we do have some loss. We've got some temperature in the exhaust gases, I'm sure. So we're heating this stuff up. So we're generating our high temperature, high pressure vapor up here. And notice what we can do is we can take some of this vapor into this hot water generator. Okay, so we can, we're basically making steam down here. I mean, it's not a standard boiler because we got this lithium bromide water solution, but we're heating it up. So we're generating, 350 degree steam at, I don't know, probably 115, 120 PSI. So, I mean, you can heat hot water with that just fine all day long. And so if you want to heat some hot water, you can buy this option on this thing. You put cold water in here, you get hot water. You can get really hot water too. I mean, if I got 350 degrees, I can get probably 300 degree water out of this thing. And I could use it for all sorts of stuff. I mean, I could use this for domestic hot water in a building. Maybe if I put one of these chillers in, I don't have to put a boiler in. Maybe this serves both, depending on capacities, okay? So that's an interesting option. And then, of course, then also I got the hot saturated steam going over here to the low temperature generator just as before. So that's the difference over here is I'm just generating my higher pressure, higher temperature steam right here. And that's part of the chiller. Okay. So let's read his notes. Let's see. Pretty good. Okay. So diagram horizon, two-stage direct fired chiller. Instead of steam-fired first-stage generator, we use natural gas burner directly. In addition, notice that we have an option for auxiliary heating. With the auxiliary heating option, you can do simultaneous heating and cooling or heating only. You could not run the chiller side. When you're in the simultaneous mode, you can set a priority between heating and cooling. Temperatures from 140 to 180 degrees can produce with this auxiliary bundle. Okay, I would have thought you'd get hotter, but I guess not. But still, 140, 180, that's good enough for building heat or domestic hot water. And this thing on setting priority, which means you can let the capacity of the system be determined by the heating requirement or the cooling requirement. So, if you set it, say, on the cooling requirement, then you just get however much heat out of it you can get out of it. If you set it on heating requirement, then that's what the controls hone in on, and you just get whatever cooling is available at that level of fire. So that's what that's referring to. Okay, so this shows for the Train product range what tonnages are available. So we see the single stage classic, the oldie but the goodie, except for the 0.65 COP. 100 says 101. I wonder if that's a typo. It's probably doesn't matter, but I think that probably should say 100 to 1660 tons, and 1660 tons is a big chiller. Okay, now remember, What's a ton? A ton of cooling is 12,000 BTUs per hour. So you take tons times 12,000, that gives you BTUs per hour of cooling capacity. Okay, and then we got a two-stage direct fired horizon from 380 to 750. Let's see, we got a KTE direct fired 100 to 300, and then they have another size range 8 to 1100, and then two-stage steam fired horizon 380 to 1150. So that is, you know, pretty good selection range. And these slides have been out there a while. I mean, there may be more options today. Questions? Yoo-hoo. Anybody got a question? You can hop on. If not, we will kill this presentation and go to the next one. Okie dokie. Not hearing anything. Now, let's get rid of that. Here, let's go back up. I wonder what that little ding was. You think somebody? No, I don't see it. Okay. Okay. So I'm pretty sure I emailed this out when I emailed out the other one, but this is where we go through kind of an economic analysis and try to make up a scenario where one of these absorbers would make sense economically. Now, I mentioned before, and they don't address it here because, you know, Trane is looking pretty much at commercial, you know, just large building campus type air conditioning situations. But in the industrial world, when you have if you have free waste heat, I mean, if I've got a huge stack and I got a big process and I'm putting up millions and millions of BTUs per hour at say 300 degrees, I mean, I don't care what the COP is. Who cares if I'm going to fuel it with free energy? The only thing that affects me is the worse the COP, the bigger the heat exchanger I got to put in, you know, because I got to provide more heat to the chiller itself. But I mean, and you see these things in industry that have lots of, you know, big industries, big footprints that have lots of energy requirements that generate lots of waste heat. That's where these things have a tremendous advantage. And you know, Matt, if you can get 350 degree waste heat to get the two-stage machine, you know, you even pick up, you know, better COPs, smaller pumps, and, you know, there's some advantages to that. Okay, so let's head on through this guy a little bit. So economics of gas cooling. Gas cooling is a growing trend across the country. Well, maybe it is, I don't know. I still don't see too many of these things. We will cover the basics of gas cooling. As electric utility rates become increasingly complex, an analysis of gas cooling becomes more complex. During this presentation, we'll go through the analysis process, particularly for a hybrid system. By hybrid system, they mean one where you have absorption and centrifugal chillers teamed together in the same situation. In these rates, I mean, I think we've, I'm doing some of this in both classes, so I kind of forget what I've told in one class and not the other class. But, you know, we've got time of day, we've got on-peak, off-peak periods, and we've got seasonal situations. So the most expensive time is going to be on-peak in the summertime. I mean, at least in this part of the world. Now, if you're in Siberia, okay, that's probably not true. It's probably going to be during the heating season, but in any place around, you know, the central portion of the United States on down to the south and even up north further than here, the system, the utility grids all peak. Their biggest peaks of the year are during cooling, hot because everybody's running air conditioning. And so they're going to make it more expensive. So that's kind of the play that this is looking at, is being able to have an absorption unit to reduce your demand, your electrical demand charges during the peak hours of the day. So that's kind of where this is going. Okay, so types of equipment: single stage indirect fired, so that would be provided with hot water or low pressure steam. Two-stage indirect fired, again, provided with 350 to 400 degree water or 350, 400 degree steam. And then double effect direct fire absorption. So those are the three that we're going to look at and run the analysis on in this presentation. Okay, so we'll spend a little time here. Single stage steam driven. Okay, so ton range, basically 100, 1,600 tons. Hot water, 295 to 270. Low pressure steam, 12 PSI. And let me see, I wanted to pull something up here. So let's look at this. It's 12. So that's 12, that's PSIG. And this is just a little steam properties calculator that I keep. So saturated steam, US units, pressure. And so if I put it there right now, this is setting on liquid, but the temperature won't change. So if it's 12 PSIG, if I figure atmospheric at 14.7, then it's going to be 26.7, right? Because when I go to the steam tables, I have to use absolute. Not absolute temperature, but absolute pressure. Okay, and so then you click calculate, bingo. So you see about 244. So the steam that they're talking about is 244. And we can notice the enthalpy because the heat that gets transferred from the steam is the heat of condensation. Okay, that's how they're going to size this thing. They're going to put in saturated steam. So if we look at the vapor, what is that? Enthalpy is 1161.84. 1161.84. And I'm just going to see what how much we get when we condense it, because we don't get all of that because the liquid still has a fair amount. So when I look at liquid, it's 212.24 minus 212.24. So we get about 900, it's 949.6. So we get about 950 BTUs of energy out of each pound of steam that we condense. So we can remember that 950 here, okay. So COP, quoting at 0.67, and this is the steam requirement, okay? So we're saying 18.7 pounds of steam required for a ton hour of refrigeration. Now think about that ton hour. Remember, a ton is BTUs per hour. So a ton is a rate. A ton is not an amount. We always have, you know, when we're dealing with these energy flows, we always have to be clear. Okay, you know, you can't say that an amount equals a rate. If you do, you're screwed up. You know, it's like saying that a degree Fahrenheit equals a PSI. You know, they're different birds. Okay, so a 1 ton hour refrigeration is 12,000 BTUs, right? Because it's a rate of 12,000 BTUs for 1 hour. So it's 12,000 BTUs, okay, an amount. Okay, so if we need 18.7 pounds, then, and we just said we're 949.6 BTUs per pound. I'm gonna store that away. I'm gonna multiply it by 18.7. So that would say that my input energy in BTUs is 17,757.52. So I'm going to store that away. Now, let me calculate, see what I get based on this for the COP. So if I take 12,000 and divide it by that 17,758, that should give me the COP, right? Because that's cooling effect divided by energy input. So 12,000 divided by recall 2, 0.6757. So it really rounds, according to this calculation, it rounds to 0.68. But, you know, in these things, they might be playing a little fast and loose. So anyway, so that looks about right. So the 18.7 matches pretty well with the 0.67 and the pressure of steam. Okay, what's a therm? I don't know if we've talked about a therm. I think I probably mentioned it, but a therm is 100,000 BTUs. Okay, and so in a million BTUs, and we oftentimes like to talk about fuel prices per million BTUs. Okay, well, if a therm is 100,000, guess what? There's 10 therms in a million, because 100,000 times 10 is a million. Okay, so let's see. So we're saying this, let's see, we need 0.24 therms of natural gas per ton hour. And I think, yeah, this is assuming when you utilize natural gas boilers. So they're assuming that we have a separate boiler here. Okay. Well, gosh, what's the efficiency of the boiler? Just, you know, energy guys like to check their numbers. So let's see. Per ton hour, we got to have 24,000 BTUs an hour. And in the steam, we had 17,758. So if I divide that by 24,000, that comes out 0.74. I don't know where they got that. But anyway, that's what it looks like they're using for a boiler efficiency. Not that you really care, but I mean, you could, if you were doing an analysis, say, hey, we got an 85% efficient boiler. And so you could modify, you could kind of go back and parrot this analysis back, but you could modify the numbers because, you know, I mean, if our required input is in the steam, the thermal energy is 17,758 divided by 0.85, that's about 20,900. So that's like 0.209 therms. So, you know, depending on the efficiency of your boiler, you could modify this. Okay, so it's, you know, I want to spend enough time so that you get comfortable with these numbers. That's one of the goals of all of this when you get to these senior level classes and all. Y'all are going to be out there doing work, and this stuff has to become a part of you so that you're really comfortable with it. You know, otherwise you're going to be out there on the job and you're going to go, oh crap, I don't remember that, I don't remember that. You know, the first 6 months, you're not very productive and you're pretty frustrated. And, you know, I mean, everybody understands, but it's better if you have become comfortable with some of this. So basically, for this scenario, we're saying that to produce this 12,000 BTUs of cooling, we have to put in 24,000 BTUs of natural gas, of energy in the gas. And then we have to burn the gas. We've got losses associated with that. And then we have to put that energy into the chiller. And we only have a 0.67 COP. So a lot of energy input to make this thing go. Okay, and so here's just, they show kind of what they think a typical setup might look like. And of course, it's going to be more complicated with it than this, but you know, these are the big components. You know, you got your boiler providing your steam to the generator, and you got your cooling tower out here. cooling what? The absorber first and then the condenser. And we've got what? Instead of 10, we've got an 18-degree delta T on this cooling tower. So don't forget that cooling tower is going to have to get bigger than if it was a centrifugal. All right. And there's a picture. I bet that's a train picture. Yep, you can see the emblem over there on the side. But so all of those stuff, the generator, the absorber, the pumps, I mean, everything is inside that basic unit. Okay. Okay, so here's the two-stage steam driven. Well, they've been around since the 70s. The single stage have been around since the 50s, that slide said. Size range 300 to 1150. High pressure steam, 115. We can play with our steam. So what is that, 115, about 130, 129.7, right? 129.7, 115, I think that's right. So on the liquid side, yeah, that's 347. And here we can check the enthalpies too. This is the liquid, 318.3. And then we get the vapor. Vapor is what? Enthalpy 1192.1. Okay, so at 115 psi G, when we condense a pound of steam, we get about 874 BTUs. So say that's what's happening as you go up in pressure, that saturation dome gets skinnier, and so when you go up to really higher and higher pressures, you may only get 600-700 pounds of steam when you condense, okay? Because there's a lot more energy in the liquid, in the condensate, because it's so hot. Okay. So here COP is 1.2. Okay. And so now let's see, we're assuming the gas boiler. I think the efficiency on this one, I think I worked out a 80 efficiency. We can check it. But let's see. So anyway, COP 1.2. So 9.7 pounds of steam per ton hour. And the gas input to the boiler is 0.125 therms, or that's 12,500 BTUs. Because again, a therm is 100,000. So you take 0.125 times 100,000 and you get 12,500. So in terms of gas, in terms of generating the steam, what's the COP of this thing? Well, it's 12,000. That's what I get out. That's my cooling effect divided by 12,500. So that's 0.96. So if you consider the COP, the boiler inefficiency into the calculation, instead of 1.2, you get 0.96. So that's pretty good. Here's my pressure. I don't think there's anything there we haven't said. Okay, and this just shows, got another one of these little diagrams. Pretty much the same thing. It's just a more expensive, more complex chiller. There's a picture. Yeah, it looks like it's getting more complicated, doesn't it? For sure. Okay, here's the two-stage direct fired, 100 to 1100 tons. So we can fire with natural gas, we can fire with propane, or we can fire with number 2 fuel oil. So a good question, you know, on a test sometime is, what's number 2 fuel oil? And that's diesel. Number 2 fuel oil is diesel, light oil, and without the additives. Now, the diesel trucks, they get a bunch of additives put in there, you know, because it's going to be burned in a diesel engine. If you're going to burn fuel in a boiler, you don't need all those additives, and so you don't pay for that. So this is a little bit cheaper. As the number on the fuel oil goes up, the viscosity goes up. A common, well, not too common, but a fairly common boiler fuel is number 6. Number 6 fuel oil will not flow if you don't heat it. It will turn into like molasses in the pipes if you get it cold. And so the higher the number, the bigger the pain in the rear it is to utilize, the more viscous it becomes, and the cheaper it becomes. So number 6, you can buy low sulfur or you can buy high sulfur. And of course, high sulfur is cheaper than low sulfur because you probably have to do something to remove the sulfur dioxide, sulfur compounds from your exhaust gases when you burn it. But this number 6 stuff, which they're not gonna design one of these things for number 6. I think the number is about 175 degrees. So all of your pipes that carry number 6, you have to do steam tracing. You put steam lines or electric or something around there, and then put insulation over it so that you can heat it to 175, 180 degrees so that you can pump it. And of course, you know, if that heat tracing in the dead of winter ever goes bad, you can be in big trouble. You know, this stuff will basically almost solidify. It depends on the temperature. I don't know at what point number 6 actually becomes almost like a solid, but if you don't heat it, you can't effectively pump it, and so that's an issue. Anyway, a little free information there. This direct fire, as we've seen, can provide both heating and cooling. COP of 1.03, and we see that that's 1.16 therms of gas per ton hour, or that's 11,600 BTUs of gas. So if you take 11.6 and divide by 12,000, you're going to get 1.03. I'll verify that here. Or 1 over that. Yeah, it's the other way, sorry. Yeah, it's 1.03. Okay. These came about in the late 80s. Natural gas, I think we said all that stuff, so we're good on that. Yeah, we're doing here. We'll do a couple more and then we'll shut down for the day. Kind of what it looks like, you know. You got well, they don't show a natural gas line, but you obviously, well, they show a fuel supply arrow. So you got to bring in your gas and your combustion air and support the combustion process. You do have stack emissions. You would probably have NOx compounds. You wouldn't have any sulfur to deal with, but you could probably would generate some NOx, NO, NO2, N2O, those sorts of compounds that there are permit regulations on. So you might have to do some stack testing periodically to make sure that you're within your permit. Cooling tower and system load, that's your chill water pumping around in a circle. And they don't show a hot water circuit on here, which they could. There's a picture. See, it's just like having a little baby boiler over here attached to the side of your chiller. That's a pretty good picture. I like that picture. See, there's your combustion air fan, and there's your flame coming out through here, and then the hot gases circulate back and forth, and bingo. There you go. Cool stuff. Okay, let's look at operating cost. So now we're going to get into doing an economic analysis on this. So let's see, single stage is 0.24 and capital T is therms. So it's 0.24 therms per ton hour. And we're going to speculate here, they're using 45 cents or $0.45 per therm. And so you just multiply that out, so you get $0.108 per ton hour of refrigeration. And don't forget, there's 10 therms to a million, and so this gas price is $4.50 a million BTUs, which is a pretty good gas price for today. I was noticing, I had some financial show up in there in the office, and I think natural gas is selling someplace around $2.85 in the fields, about $2.85 a million. And then, you know, you got to have distribution, and everybody along the way has got to add their tax to it. So everybody's got to make a profit. And so, you know, we're seeing $3.50 to $4. $4.50 is certainly possible. And I'm paying $8, $9 at my house. So, you know, I'd be happy to have gas at 45 cents a therm. Okay, at any rate. So then for the two stage, we're 0.125 therms per ton hour. So that's 0.56, and direct fired is 0.116, so that's 0.052, and the centrifugal, now this is kind of interesting, because of the COP, and okay, so let's calculate the COP. Okay, so it says it takes 0.6 kilowatt hours to produce a ton hour of refrigeration. So the kilowatt hour is 3412 or 3413. You see it both ways. I'm going to use 3413 times 0.6. So that's 2,047.8 BTUs. And so I'm going to get 12,000 BTUs of cooling for that. So 12,000 divided by 2,000, say 48, what it rounds to, is 5.86, between 5 and 6. So that COP on that centrifugal is pushing 6. Well, heck yeah, that's pretty darn efficient. So if you're just looking at straight operating costs, the conclusion is you may not save money simply moving BTUs of cooling from electric to gas. Now, if you got waste heat, it's free. You know, all you got to do is worry about, you know, doing the project and putting in the heat exchangers and, you know, buying the chiller and all that stuff. So you do have to worry about that. Okay. Average electrical rate of 8 cents. Yeah, did we have? Yeah, we had that up here. Okay, well, let's see what the cost per million BTUs is for 8-cent electricity. So what you do, you get out your calculator and you put in a million, and you divide it by 3413, because that's the conversion between BTUs and kilowatt hours. And that comes up say 293, and then you multiply that times 0.08. So that electricity, just, on a million BTU basis, is $23.44. So we can buy natural gas for $4.50 a million. And when we buy electricity, it costs us $23.44 a million. Store two. So that's kind of interesting. So the ratio there, if I take the 23.44 divided by 4.5, 5.2. So electricity is 5.2 times more expensive to purchase on an equal energy footing. But that centrifugal chiller has a COP of 5.86, which really levels the playing field. Okay, so it's kind of interesting how all this works out. Let's see here. What are we going to? Oh, is that it? Yeah. All right, so I tell you what, I think this is a good stopping point. So what I'll do is we'll cut off here, and I'll send you all those links. I mean, you have all of the links for the videos that we're going to have the quiz on Thursday, but I will send you one more. But if you haven't watched them all, you can get started immediately because you can find the links already on your email. But I'll send you a summary page, and I would expect no more than a 30-minute test, which, they're just going to be multiple choice, maybe true, false, something like that. So if you figure 30 questions, a minute each, there'd be something like that. So anyway, but I do want you watching those videos. Okay, so I'm going to stop the record and then cut this off, and we will continue on after the quiz on Thursday. Bye-bye. Hope everybody has a good day.